Grab a ruler and try to trace a circle. You can't. You get a stiff little polygon, corner, 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 never a smooth curve. A straight edge can only ever draw straight things. Early AI hit this exact wall. Stack 100 layers of pure math, and the whole tower could still only draw one straight line. Then someone added one tiny bend, and suddenly the same network could trace almost any shape in the world. In the next few minutes, you'll see exactly why that one bend changes everything. This is Glass Box, where we make the hardest ideas in AI feel obvious. Today's question: what is the one small ingredient that lets a neural network learn curvy, twisty, real-world patterns instead of just straight lines? Quick recap from the earlier videos. A neuron takes its inputs, multiplies each by a weight, adds a bias, and fires. We've watched layers stack and the knobs get tuned, but we glossed over one little step at the end of each neuron, that gentle squeeze from video 1 that crushed the total into a number between 0 and 1. That squeeze is exactly the bend we're about to meet. Same step, just seen a new way, and it's the whole story today. Here's the plan in 5 steps. 1. What a straight line really is. 2. Why stacking straight lines stays straight. 3. The bend itself. 4. How one bend folds flat space into a curve. And 5. How stacking bends lets a network fit literally any pattern. Part 1. What a straight line really is. Picture a single input going into a neuron, say, the temperature outside. The neuron multiplies it by a weight and adds a bias. Plot the output against the input, and you always get the same shape, a perfectly straight line. That word linear just means straight, no curves allowed. Turn the weight up, the line tilts steeper. Turn it down, it flattens. Change the bias, the whole line slides up or down, but it stays a line every time. Real example, like a flat ramp. You can make it steeper or gentler, raise it or lower it, but a ramp is always flat. It can never bulge into a hill. And that's the catch. The real world is full of curves, the path of a thrown ball, the line between a cat photo and a dog photo, a spam email versus a real one. None of those are straight. A ruler will never trace them. Part 2. Why stacking straight lines stays straight. Now you might think, fine, one line is weak, but we stack layers, feed a line into another line, into another. Surely all that stacking buys us a curve, right? Here's the gut punch. It doesn't. Take a straight line and feed it into another straight line, and the result is just one more straight line. Do it 1,000 times and you still end up with a single straight line. The depth collapses. Real example, like stacking flat ramps end to end. Each one is flat, so the whole thing is still just one long flat ramp. You can lay down 1,000,000 of them and you'll never get a single curve. Stacking flat on flat only ever gives you flat. So all those extra layers, all those billions of knobs would be wasted. Mathematically, the entire deep network would be no smarter than a single neuron. That is the wall early networks slammed into. Something has to break the straightness. Part 3. The bend. The fix is shockingly small. After each neuron does its multiply and add, we pass that number through one extra step that is allowed to be not straight. We put a little kink in the line. That kink is called an activation function. An activation function is just a tiny rule applied to each neuron's output that introduces a bend, a place where the line is allowed to change direction. Without it, everything stays linear. With it, the network can curve. Real example, like a hinge in the middle of that flat ramp. The two halves are still straight, but now the ramp can fold. One hinge and flat becomes not flat. The most popular bend in all of AI is almost laughably simple. It's called ReLU, and the whole rule is, if the number is positive, let it pass through unchanged. If it's negative, replace it with 0. That's it. Good news flows, bad news gets muted to nothing. Real example, like a one-way valve or a friend who only ever passes along the good news and quietly drops the bad. Plotted out, it's a flat floor that suddenly kicks upward, one clean elbow. There's an older, gentler bend too, called the sigmoid. Instead of a sharp elbow, it's a smooth S-shaped curve that eases any number into a value between 0 and 1. Real example, like a dimmer switch sliding from off to on, no jump, just a smooth ramp up and a smooth ease off at the top. Same job as ReLU, break the straightness. ReLU just does it with a crisp corner, and these days it usually wins because it's faster and simpler. Part 4. How one bend folds flat space. Here's where it gets beautiful. Imagine the network's input as a flat sheet of paper with dots scattered on it that we want to separate. A straight-line network can only slice that sheet with one straight cut. Often, that's just not enough. Now add a bend. That ReLU elbow effectively folds the sheet of paper along a crease. Points that were far apart can now sit right on top of each other. A shape that was impossible to cut with one straight line suddenly lines up so a single cut works. Real example, like folding paper to cut a perfect heart or snowflake. One straight snip on folded paper opens into a curvy, symmetric shape you could never cut on a flat sheet. The fold is doing the hard part. The bend is the fold. Part 5. Stack the bends, fit anything. Now the payoff. One bend gives you one fold, one corner, but every neuron in every layer adds its own little bend in its own place. Dozens of them, thousands of them. Each kink is small, but together they're a master sculptor. Watch what happens. We start with a flat line trying to fit a wavy set of dots, hopeless. Switch the bends on, and tiny kink by tiny kink, the line buckles and curves until it threads right through every point. The same machinery that could only draw a ruler is now tracing a smooth, complicated curve. And this is a genuine, proven result. With enough of these little bends, a network can approximate basically any pattern you can draw. Curves, loops, spirals, the messy boundary between cats and dogs. Every shape is just a sum of enough tiny bends. That is why the bend matters more than almost anything else in the network. So here's the whole picture. A straight line is a ruler useful, but it can't curve. Stack rulers and you still just get a ruler. The depth collapses. The fix is one tiny bend after each neuron, ReLU's crisp elbow or Sigmoid's smooth S. That one bend folds flat space into a curve, and stacking thousands of bends lets the network trace almost any pattern in the world. No bend, no learning curves. That little kink is what makes deep learning deep. But notice, at the very end, the network spits out a pile of raw scores. How cattish, how doggish, how three-ish this thing looks. So how does it turn those messy numbers into a confident answer with an actual percentage of how sure it is? That's exactly the next video. How AI decides how sure it is. If that one little bend finally made deep learning click, subscribe so you don't miss it. This was Glass Box. See you in the next one.